transformer's capacity hinges on its kilovolt ampere, or kVA, rating. This rating is derived from the formula kVA equals volts times amps. In a scenario involving a 125 amp, 45 kVA transformer, we can infer the voltage by dividing the kVA by the amperage, yielding 360 volts. To ascertain whether an upgrade is necessary, a crucial step involves calculating the panel's current draw. A 208 volt, 100 amp panel is capable of drawing up to 20.8 kilowatts of power. This is calculated by multiplying the voltage 208 volts by the current 100 amps, which equals 20.8 kilowatts. Based on this panel load calculation, the required transformer capacity is determined by the formula kVA equals kilowatts divided by the power factor. Assuming a power factor of 0.8, the calculation would be 20.8 kilowatts divided by 0.8, resulting in 26 kVA. Therefore, a 26 kVA transformer would likely suffice for powering the existing panel. However, anticipating future load increases of the addition of equipment demanding higher amperage warrants considering an upgrade to a transformer with a higher kVA rating. The amperage rating of a transformer is intertwined with its kVA rating and voltage. For instance, a 26 kVA transformer with a 360 volt primary voltage would have an amperage rating calculated by dividing the kVA by the voltage, equating to 26 kVA divided by 360 volts, which equals approximately 72.2 amps. Consequently, if opting for a 26 kVA transformer, one would require a 72.2 amp transformer. Consulting with a qualified electrician is paramount in determining the appropriate transformer size and amperage tailored to specific needs. Firstly, it's essential to understand that electrical panels are designed with a maximum amperage capacity, often indicated on the panel's main breaker or nameplate. This rating represents the highest amount of electrical current the panel can safely handle. Secondly, exceeding this capacity can lead to serious consequences, including overheating, trip breakers, and potentially electrical fires. Therefore, it's crucial to stay within the panel specified limits. Thirdly, the total load on an electrical panel is the sum of all the individual circuits and appliances connected to it. This includes lighting, outlets, HVAC systems, and any other electrical devices. Fourthly, to determine the total load, you need to calculate the amperage draw of each circuit. This information can usually be found in the appliance's nameplate or in the electrical plans. Fifthly, if the calculated total load exceeds the panel's amperage rating, it indicates that the panel is overloaded. In this situation, it's necessary to either reduce the load or upgrade the panel to a higher amperage capacity. Sixthly, upgrading a panel typically involves replacing the existing panel with a new one that has a higher amperage rating. This also requires upgrading the wiring and other components to ensure they can handle the increased current. Seventhly, it's important to note that upgrading an electrical panel is not a do-it-yourself project. It requires the expertise of a qualified electrician who can safely disconnect the power, install the new panel, and ensure that all connections are properly made. Eighthly, in addition to upgrading the panel, it may also be necessary to upgrade the transformer that supplies power to the building. This is especially true if the existing transformer is not large enough to handle the increased load. Ninthly, the size of the transformer is determined by the total kVA load of the building. This includes the electrical panel, as well as any other electrical equipment that is connected to the transformer. Tenthly, if the existing transformer is undersized, it can lead to voltage drops, overheating, and potentially damage to the transformer. Therefore, it's crucial to ensure that the transformer is properly sized to handle the total load of the building. The voltage drop across a conductor is directly proportional to the current flowing through it and the conductor's impedance. To minimize voltage drop, consider the following. Firstly, use conductors with larger cross-sectional areas as they offer low resistance. Secondly, shorten the length of the conductors to reduce the overall impedance. Thirdly, select conductors with materials that have lower resistivity, such as copper or aluminum. Fourthly, ensure proper connections and terminations to minimize contact resistance. Fifthly, maintain a balanced load distribution to prevent excessive current flow in any one conductor. Sixthly, consider using voltage regulators or transformers to compensate for voltage drops in long distribution lines. Seventhly, regularly inspect and maintain electrical systems to identify and address any potential issues that may contribute to voltage drops. Eighthly, calculate the expected voltage drop using appropriate formulas and software tools to ensure it remains within acceptable limits. Ninthly, comply with relevant electrical codes and standards that specify voltage drop limits for different applications. Tenthly, consult with qualified electrical engineers or contractors for complex or critical installations to ensure optimal voltage drop management. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is not doing useful work, leading to increased energy costs and potential equipment problems. To improve power factor, firstly, install power factor correction capacitors to offset the reactive power component of the load. Secondly, avoid operating motors and transformers at light loads, as this can lead to a decrease in power factor. Thirdly, use energy-efficient equipment with high power factors to reduce overall reactive power demand. Fourthly, regularly monitor power factor and implement corrective measures as needed. Fifthly, optimize the operation of inductive loads such as motors and transformers to minimize reactive power consumption. Sixthly, consider using synchronous condensers or static VAR compensators for large industrial facilities. Seventhly, ensure proper sizing of electrical equipment to match the load requirements. Eighthly, avoid excessive voltage fluctuations, which can negatively impact power factor. Ninthly, educate employees on the importance of power factor and energy conservation practices. Tenthly, consult with power quality experts to conduct a thorough assessment and recommend customized solutions for improving power factor. Harmonics are distortions in the voltage and current waveforms that can cause a variety of problems in electrical systems. These distortions are typically caused by nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. To mitigate harmonics, firstly, install harmonic filters to block or reduce the flow of harmonic currents. Secondly, use line reactors or isolation transformers to reduce the impact of harmonic currents on the power supply. Thirdly, implement power factor correction capacitors to mitigate the effects of harmonics on power factor. Fourthly, specify harmonic resistant equipment for new installations to minimize harmonic generation. Fifthly, regularly monitor harmonic levels and implement corrective measures as needed. Sixthly, apply active harmonic filters to dynamically compensate for harmonic currents. Seventhly, use tuned filters to target specific harmonic frequencies. Eighthly, ensure proper grounding and shielding to minimize the propagation of harmonic currents. Ninthly, design electrical systems with sufficient capacity to handle harmonic loads. Tenthly, consult with power quality experts to conduct a comprehensive harmonic analysis and recommend appropriate mitigation strategies. Electrical grounding is a critical safety measure that provides a path for fault currents to flow back to the source, tripping circuit breakers and preventing electrical shock hazards. A properly grounded electrical system helps to protect people and equipment from electrical faults and surges. Here's how electrical grounding works. Firstly, a grounding electrode, typically a ground rod or a metal water pipe, is connected to the earth to provide a low resistance path to ground. Secondly, the grounding electrode is connected to the electrical panel and other metal enclosures, providing a path for fault currents to flow back to the source. Thirdly, when a fault occurs, such as a short circuit, the fault current flows through the grounding system back to the source, tripping the circuit breaker and disconnecting the power supply. Fourthly, this process prevents the metal enclosures from becoming energized, reducing the risk of electrical shock. Fifthly, electrical codes and standards specify the requirements for grounding electrical systems to ensure safety and effectiveness. Sixthly, grounding also helps to protect electronic equipment from damage caused by voltage surges and transients. Seventhly, regular inspection and testing of grounding systems are essential to ensure their integrity and effectiveness. Eighthly, grounding conductors should be properly sized and installed to provide a low impedance path for fault currents. Ninthly, grounding systems should be designed to minimize the risk of ground loops, which can cause noise and interference in electronic equipment. Tenthly, consult with qualified electricians or electrical engineers for complex grounding installations to ensure compliance with codes and standards. Overcurrent protection devices, such as circuit breakers and fuses, are essential components of electrical systems that protect against overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of electrical fires. Here's how overcurrent protection devices work. Firstly, circuit breakers are electromechanical devices that trip and interrupt the flow of current when an overcurrent condition is detected. Secondly, fuses are one-time devices that melt and break the circuit when an overcurrent condition is detected. Thirdly, circuit breakers can be reset after they trip, while fuses must be replaced. Fourthly, overcurrent protection devices are rated in amps, indicating the maximum current they can carry without tripping or blowing. Fifthly, the ampacity of the overcurrent protection device should be matched to the ampacity of the circuit conductors to provide adequate protection. Sixthly, overcurrent protection devices should be selected based on the specific application and the type of load being protected. Seventhly, electrical codes and standards specify the requirements for overcurrent protection in electrical systems. Eighthly, regular inspection and testing of overcurrent protection devices are essential to ensure their proper functioning. Ninthly, overcurrent protection devices should be installed in readily accessible locations for easy maintenance and replacement. Tenthly, consult with qualified electricians or electrical engineers for complex overcurrent protection installations to ensure compliance with codes and standards. Surge protection devices, or SPDs, are designed to protect electrical and electronic equipment from voltage surges or transient overvoltages. These surges can be caused by lightning strikes, power grid switching, or internal equipment malfunctions. SPD divert the surge current away from the protected equipment, preventing damage and downtime. Here's how surge protection devices work. Firstly, SPD are typically installed at the service entrance of a building or at individual equipment locations. Secondly, when a voltage surge occurs, the SPD detects the overvoltage condition and provides a low impedance path for the surge current to flow to ground. Thirdly, this diverts the surge current away from the protected equipment, preventing damage to sensitive electronic components. Fourthly, SPD are rated by their surge current capacity, indicating the maximum amount of surge current they can handle. Fifthly, SPD can be either single-use or multi-use devices, depending on their design and construction. Sixthly, electrical codes and standards specify the requirements for surge protection in electrical systems. Seventhly, surge protection should be considered for all types of electrical and electronic equipment, especially sensitive devices like computers, televisions, and appliances. Eighthly, regular inspection and testing of SPD are essential to ensure their proper functioning. Ninthly, SPD should be installed in readily accessible locations for easy maintenance and replacement. Tenthly, consult with qualified electricians or electrical engineers for complex surge protection installations to ensure compliance with codes and standards. A qualified electrician can assess the existing electrical system, calculate the loads, and determine the appropriate size and type of transformer and panel to meet current and future needs. They can also ensure that the installation complies with all applicable electrical codes and standards, ensuring the safety and reliability of the electrical system. A detailed load calculation involves determining the total electrical demand of a building or facility. It is an essential step in designing and sizing electrical systems to ensure they can safely and reliably supply power to all connected loads. A load calculation typically includes the following steps. Firstly, identify all the electrical loads in the building, including lighting, receptacles, appliances, HVAC equipment, and any other electrical devices. Secondly, determine the demand factor for each load, which is the percentage of the total load that is expected to be in use at any given time. Thirdly, multiply the connected load by the demand factor to determine the demand load for each load. Fourthly, sum the demand loads for all the loads to determine the total demand load for the building. Fifthly, apply any applicable diversity factors, which account for the fact that not all loads will be operating at their maximum demand simultaneously. Sixthly, add any additional loads, such as spare capacity or future expansion, to the total demand load. Seventhly, the total demand load is then used to size the electrical service, transformer, panel boards, and other electrical equipment. Eighthly, load calculations should be performed in accordance with applicable electrical codes and standards. Ninthly, accurate load calculations are essential for ensuring the safety and reliability of electrical systems. Tenthly, consult with qualified electrical engineers or electricians for complex load calculations to ensure accurate results and compliance with codes and standards. The electrical codes and standards are a set of rules and regulations that govern the design, installation, and maintenance of electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association, or NFPA, the Institute of Electrical and Electronics Engineers, or IE, and the American National Standards Institute, or ANSI. Electrical codes and standards are designed to ensure the safety of people and property from electrical hazards. They cover a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with electrical codes and standards is mandatory in most jurisdictions. Electrical codes and standards are constantly evolving to keep pace with technological advancements and changing safety requirements. It is important for electricians and electrical engineers to stay up to date on the latest codes and standards to ensure that their work is safe and compliant. Electrical codes and standards are essential for ensuring the safety and reliability of electrical systems. Failure to comply with these codes and standards can result in serious consequences, including electrical shocks, fires, and property damage. The National Electrical Code, or NEC, is a widely adopted electrical code in the United States. It provides comprehensive guidelines for electrical installations, covering everything from wiring methods to grounding and overcurrent protection. The NEC is updated every 3 years to reflect the latest technological advancements and safety requirements. The NEC is organized into chapters, articles, and sections, making it easy to find specific information on electrical installations. The NEC is an essential resource for electricians, electrical engineers, and anyone involved in the design, installation, or maintenance of electrical systems. The NEC is not a law, but it is adopted by many state and local jurisdictions as part of their electrical codes. Compliance with the NEC is essential for ensuring the safety of electrical installations. The NEC provides detailed requirements for wiring methods, including conductor types, sizes, and installation methods. The NEC also specifies the requirements for overcurrent protection, including circuit breakers and fuses. The NEC provides guidelines for grounding electrical systems to ensure safety and prevent electrical shocks. The NEC is a complex and comprehensive document, but it is essential for ensuring the safety and reliability of electrical systems. The NEC is available for purchase from the National Fire Protection Association, or NFPA. The NEC is also available online through various subscription services. Electrical permits are required for many types of electrical work to ensure that the work is performed safely and in compliance with applicable electrical codes and standards. Electrical permits are typically issued by local government agencies, such as city or county building departments. Electrical permits are required for new electrical installations, alterations to existing electrical systems, and repairs to damaged electrical systems. The purpose of electrical permits is to protect the public from electrical hazards. Electrical permits ensure that electrical work is inspected by qualified electrical inspectors. Electrical inspectors verify that the work is performed in accordance with applicable electrical codes and standards. Electrical permits help to prevent electrical fires, electrical shocks, and other electrical hazards. Electrical permits also help to ensure that electrical systems are properly grounded, protected from overcurrent, and installed with the correct wiring methods. Obtaining an electrical permit typically involves submitting an application to the local government agency. The application will typically require detailed information about the proposed electrical work. The local government agency will review the application and issue a permit if the proposed work meets the requirements of the applicable electrical codes and standards. Electrical inspectors will typically inspect the electrical work at various stages of completion. The electrical inspector will verify that the work is performed in accordance with the permit and the applicable electrical codes and standards. Failure to obtain an electrical permit or to comply with the requirements of the permit can result in fines, penalties, and delays in the project. Electrical inspections are conducted by qualified electrical inspectors to verify that electrical work is performed safely and in compliance with applicable electrical codes and standards. Electrical inspections are typically required for new electrical installations, alterations to existing electrical systems, and repairs to damaged electrical systems. The purpose of electrical inspections is to protect the public from electrical hazards. Electrical inspections ensure that electrical systems are properly grounded, protected from overcurrent, and installed with the correct wiring methods. Electrical inspectors verify that the work is performed in accordance with the electrical permit and the applicable electrical codes and standards. Electrical inspections help to prevent electrical fires, electrical shocks, and other electrical hazards. Electrical inspectors typically inspect the electrical work at various stages of completion. The electrical inspector will verify that the work is performed in accordance with the permit and the applicable electrical codes and standards. The electrical inspector will typically issue a certificate of approval if the electrical work is found to be in compliance with the applicable electrical codes and standards. Failure to pass an electrical inspection can result in delays in the project and the need to correct any deficiencies in the electrical work. Electrical safety is of paramount importance to protect individuals and property from electrical hazards. Implementing robust safety measures is crucial in both residential and commercial settings. Here are some key electrical safety tips. Firstly, always turn off the power at the breaker before working on any electrical circuit. Secondly, use insulated tools when working with electricity. Thirdly, never overload electrical circuits or outlets. Fourthly, keep electrical cords and appliances away from water. Fifthly, inspect electrical cords and appliances regularly for damage. Sixthly, replace damaged electrical cords and appliances immediately. Seventhly, install ground fault circuit interrupters, or GFCIs, in wet locations such as bathrooms and kitchens. Eighthly, use arc fault circuit interrupters, or FCIs, to protect against electrical fires. Ninthly, have your electrical system inspected regularly by a qualified electrician. Tenthly, educate yourself and others about electrical safety. Regular maintenance of electrical systems is essential to ensure their safe and reliable operation. A well-maintained electrical system can help to prevent electrical fires, electrical shocks, and other electrical hazards. Here are some key electrical maintenance tips. Firstly, inspect electrical panels and components regularly for signs of damage or deterioration. Secondly, tighten loose connections in electrical panels and outlets. Thirdly, replace damaged or worn electrical components. Fourthly, clean electrical panels and components to remove dust and debris. Fifthly, test ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or FCIs, regularly to ensure they are functioning properly. Sixthly, trim trees and shrubs that are growing near overhead power lines. Seventhly, keep electrical panels and equipment accessible for maintenance and repairs. Eighthly, have your electrical system inspected regularly by a qualified electrician. Ninthly, keep records of all electrical maintenance and repairs. Tenthly, establish a preventive maintenance program for your electrical system. Troubleshooting electrical problems requires a systematic approach to identify the source of the issue and implement effective solutions. It is crucial to prioritize safety and follow proper procedures to avoid electrical hazards. Here are some key steps for troubleshooting electrical problems. Firstly, identify the symptoms of the electrical problem. Secondly, gather information about the electrical system. Thirdly, isolate the problem to a specific circuit or component. Fourthly, test the circuit or component using appropriate test equipment. Fifthly, analyze the test results to determine the cause of the problem. Sixthly, implement a solution to fix the problem. Seventhly, verify that the solution has resolved the problem. Eighthly, document the troubleshooting process and the solution. Ninthly, consult with a qualified electrician if you are not comfortable troubleshooting electrical problems. Tenthly, always prioritize safety when troubleshooting electrical problems.